Hi, welcome to this training video on achieve active circuit protection using eFuse. In this training, you will learn where circuit protection is needed and why it is so important. What are the common methods of circuit protection and their challenges. We will also discuss on what an eFuse is and how it simplifies the system protection. This slide shows several end equipment in personal electronics, industrial, automotive, enterprise and comms where circuit protection is needed. These electronic systems use multi-voltage power distribution bus to support various loads. One of the major expectations is the minimal system downtime during any transient abnormal events such as overload or short circuit conditions. Not only that, the system should recover from transient faults without any manual intervention. For example, any overload event can affect the power quality of the connected bus and eventually affect other connecting loads in the same bus. So today's system designers use protection devices at load side or supply side or sometimes at the both ends to protect systems against faults. Depending on application, the protection device should provide protection against short circuit currents, overload currents, reverse and inrush currents, over voltage and reverse voltages. The best way to prevent system downtime is to detect, respond to a fault, and correct potential damaging conditions as quick as possible, which means the protection device should provide active current protection. This slide shows discrete circuit protection solution which uses P-MOSFET with associated RC network for inrush current control and a fuse for overload and short circuit protection. It also uses a blocking diode for reverse polarity as well as reverse current blocking. It uses a TVC diode for surge protection. It also uses external current sense resistor with a fast comparator for achieving active circuit protection, and uses comparators with references to cut the power path during under voltage and over voltage events. Let us discuss about the challenges with these discrete solutions. These circuits use expensive PMOSFET. These solutions are bulky and inefficient. For example, a 2 amps load current results in around 1.4 watt dissipation across the series diode and a corresponding rise in board temperature. These solutions do not incorporate any protection for the FET, so the thermal design for the FET is often oversized for safety margin. The discrete circuits need more components and also occupies more board space. More components also raise concern on circuit robustness and reliability. Let's see what an eFuse is. In simple words, we can define eFuse as a circuit protection device with an integrated FET used to limit current voltages to safe levels during fault conditions. As seen in the figure, the common elements of eFuse are a switch to modulate the load current, a current sensing element usually realized with a FET, and a control logic with all the protection features. In the coming slides, I will discuss more in detail on specific protection feature of eFuse and how it simplifies circuit protection. Inrush currents are major concern in DC power systems. For example, while hot plugging a hard disk drive into a storage system, huge inrush current can result due to quickly charging its filter or load capacitor. This inrush current with fast slew rate creates disturbance to the connected voltage bus and to the other subsystems, causing an intermediate number of failures, including data corruption or logic lockups. This problem can be solved by controlling the output voltage ramp plate, thereby limiting the inrush current and the disturbance on the input voltage. Discrete circuits use RC components around the FET for inrush current control. These RC components need to be sized in consideration with the gate characteristics of the FET and the load. As seen in the below left figure, with a discrete circuit, the output voltage rises exponentially. So many times the design needs iterations to limit the inrush current within the desired limits. Whereas eFuse provides linear output voltage profile with constant inrush current. The inrush current magnitude can be adjustable easily with the external DVDT capacitor. Overcurrent protection is needed to protect the downstream circuitry from excessive currents and to avoid any potential circuit damage or fire catching. As discussed, discrete circuits use external current sense resistor with a fast comparator for overcurrent protection and often needs trade-off between accuracy, cost, and power loss. TIE fuses provide active current protection either by limiting the fault current, which is called as current limiting operation, or by breaking the fault circuit path, which is known as circuit breaker operation. The below left side image shows the current limiting function of TPS25942A device. Here the current limit is set to 5 amps. For an overload condition, the eFuse limits the input current to 5 amps until the overload is removed or the eFuse junction temperature reaches the thermal shutdown temperature, which is typically 150 degrees centigrade. Once the eFuse enters thermal shutdown, it either remains in off position or attempts to restart after auto retry delay. Since TPS25942A device is an auto retry device, it restores to normal operation when the overload fault is removed. The current limiting operation is more suitable for applications where the overcurrent event is temporary. Let's talk about the circuit breaker operation. For sensitive loads such as hard drive in data centers, immediate power path cutoff is a safe option in response to overcurrent fault. TPS25944A eFuse provides circuit breaker operation with overload timeout. When the load current exceeds the set current limit of 5 amps, the device starts the fault timer and breaks the circuit path if the load current doesn't fall below 5 amps before the fault timer expires. Since TPS25944A is an auto retry device, it attempts to restart after auto retry delay of 128 milliseconds. Circuit breaker feature essentially avoids system downtime by allowing pulsed overloads at the output for an interval of fault period, that is 4 milliseconds in case of TPS25944A device. One of the advantages of eFuse over discrete solutions is the ability to respond faster for short circuit faults. During a transient short circuit event, the current through the eFuse increases very rapidly. The current limiter amplifier of eFuse cannot respond very quickly due to its limited bandwidth. To solve this, TI eFuses incorporates a fast trip current comparator, which shuts down the FASFET very quickly when the load current Iout exceeds the fast trip current threshold I fast trip. The fast trip threshold is set at 60% higher than the programmed overload current limit. As shown in the below left figure, after the transient current is terminated, the current limit amplifier smoothly regulates the output current to the set current limit value of 5 amps. The below right side figure shows the fast trip comparator response, which is around 200 nanoseconds. Reverse current protection. Reverse currents can flow through the system when the voltage at the output is higher than at the input. In applications such as power mixing for redundant power systems or SSD with large hold-up output capacitor, there will be a risk of large reverse currents when the input power is disconnected. These reverse currents can damage internal circuitry or system power supplies if it is not limited. Let's see how this can be achieved. A series diode can block reverse currents but results in significant power loss at higher currents and needs thermal management. External MOSFET with ideal diode controller IC is more efficient option and also offers flexibility for higher current supports. However, it occupies more board space. TI TPS2594 family of eFuses integrates blocking FET and a fast reverse current comparator to provide true reverse current blocking. When the input power fail is detected, the internal FET is turned off in 1 microsecond typically. True reverse current blocking facilitates simplified, efficient power mixing in redundant power systems. Next is overvoltage protection. Transient induced voltages or inductive switchings can cause overvoltages in the system, which can last from few hundred microseconds to milliseconds. As seen in the top right side figure, discrete circuits need comparator logic with references to cut off the power path during overvoltage and undervoltage events. Coming to TI eFuse portfolio, two options are available. An eFuse with the output voltage cutoff feature guards the sensitive circuits from overvoltage by turning off the internal FET immediately. The trip point for overvoltage cutoff can be programmable through an external resistor. As seen in the left below figure, TPS25942A eFuse turns off the internal FET when the input voltage exceeds 16.5 volts, causing the output voltage Vout fall to 0. An eFuse with output voltage clamp feature clamps the output to internal OVC trip point. For example, TPS259261 has 15 volts as trip point. When the input voltage exceeds 15 volts, the internal clamping circuitry activates and limits the output voltage to typical 15 volts and serves the load. If the transient on the input is only temporary, the eFuse hides the downstream circuitry from overvoltage faults. If the fault lasts long, the eFuse may turn off due to thermal shutdown. Over temperature protection. Accurate temperature measurement in discrete solutions is challenging. So, discrete protection solutions need careful selection of FET and thermal design to keep the device in safe operating area limits under any extreme fault conditions. Whereas TI eFuses comes with built-in over temperature protection and gets shut down if the junction temperature exceeds 150 degrees centigrade. Let's see how eFuse recovers after fault. Most of the eFuses parts from TI are available in two versions, latch off and auto retry. A latch off version remains in off position and needs power recycle to turn on again. System with latch off version provides more safety by immediately isolating the faulty component, but also reduces the system uptime. The right side figure shows the short circuit response of latched device TPS25942L, where the device shut down for overcurrent fault and needs reset at enable pin to bring the device back into operation. On the other hand, an auto retry device continues to power cycle itself until the fault is cleared. The left side image shows how TPS25942A resumes to normal operation when short circuit fault is cleared. The last digit of part number indicates the type of device. A and 1 corresponds to auto retry version and L and 0 corresponds to latched version. Reverse polarity protection, where it is needed. In applications such as PLC systems, the input side needs reverse polarity protection against any field supply misfiring. One simple way to achieve is by using a combination of fuse and TVS diode, where fuse blows and protects the load against reverse polarity voltages. After the fault, the fuse needs to be replaced. A series diode can block reverse voltages, but results in power loss at higher currents and needs thermal management. PMOSFET-based discrete solution occupies more board space. It also has a risk of failure when the input power is removed, causing the output capacitor discharge through fully enhanced PMOSFET. TI eFuse TPS2660 integrates reverse polarity protection circuit and does not need any external components. It ensures the device is not functional during reverse polarity conditions and the internal FET blocks the reverse current path. Most of the TI eFuses are recognized as solid-state overcurrent protectors under UL 2367 standard. This helps in sectioning subsystems as low power circuits to expedite the UL certification for a product. TI eFuses limits currents, voltages under any single fault and are safe to use. These are recognized under UL Safety Standard 60950. Latest eFuse devices from TPS2594 family has several features which adds value to the system, such as precise load current monitoring within ±8% accuracy to monitor the health status of the system. This family of devices has power good comparator to monitor any voltage in the system within ±2% accuracy. This can eliminate the need for a separate voltage supervisor IC. The power good signal can be used for power sequencing the downstream circuitry. This family of devices also has a fault indicator to report fault condition to the central system controller for corrective action. Let's summarize what we discussed so far. Modern electronic systems need more than one type of protection. Though it can be met with discrete circuits, but often they result in occupying more board space less efficiency, slower in response, and as expensive solutions. TI integrated circuit protection solution eFuse is compact in size. Most of them are available in 3 by 3 square mm size. TI eFuses provide high degree of programmability, and these are very robust against system faults. The most advantageous is these are certified under safety UL standards and are safe to use. Several application notes are available at ti.com which provide details about using eFuse in several end equipments and their circuit configurations. TI eFuses has a design calculation tool which can help in calculating the external parameters. Several eFuses also has web-bench support to model the eFuse parameters and to optimize their performance. For more information and to view all resources, please visit the Texas Instruments eFuse homepage found at www.ti.com/eFuse. And for any questions, feel free to post on the Load Switches and Power Path Protection E2E forum. Thank you for taking time to watch this presentation.